Thank you, Laurel, and thank you, everyone, for coming out tonight. It's really an honor to be able to speak in front of the Hydro program as an alum of the program. Now, before I begin, some of you may be wondering, why does the title of this talk have to do anything with Walker River? Originally, the talk was supposed to be about hydraulic fracturing in northeastern Nevada. And unfortunately, the report that we're working on right now is not quite finished, and because of that, some of the team members felt it was a little bit too early to present some of the results. So I had to shift gears at last minute and talk about the Walker River program. But I'm very proud of the Walker River project, and there are numerous people working on it, and hopefully we'll give you some insight. This is definitely a collaborative project. I truly apologize. My graphic arts abilities didn't work out so well. There's supposed to be a UNR logo, but this is a collaborative project with the U.S. Geological Survey, UNR, the Desert Research Institute, and Ecosystem Economics. And it's really important to note that this is a collaborative project with a lot of other team members. And let's start with a few of them. I want to introduce a few of the team members. I'm really just the messenger here. These folks really did all of the heavy lifting in this project. The first is Rosemary Carroll with the Desert Research Institute. She's a groundwater modeler and created some of the upper watershed groundwater models, at least for Mason and Smith Valley. Kip Allender, he's with the U.S. Geological Survey. He created the lower Walker groundwater model. Bruce Alward, he's with Ecosystem Economics. He's our economist who keeps us straight to make sure we know exactly how much water is worth. Tim Miner, he's the GIS database developer and in charge of all of the mapping for the project. Justin Huntington, who's on top of an eddy tower here, and he is in charge of creating a lot of the evapotranspiration products for the project. And Jim Thomas, he's the program manager for the DRI side of the entire Walker Basin study. Doug Boyle with UNR, he's in charge of the paleoclimate modeling and hydrologic modeling. And Mike Colloquium is the program manager on the UNR side. This is Enrique Triana with NWH in Colorado. He is one of the lead developers for ModSim. ModSim is the water rights model that we use in the Walker Basin. And last but not least, Chris Garner of UNR. He is the one who really turns the crank on all of these models and keeps them going for us. He's the one who, day in, day out, actually runs the models for us. Okay, what I'd like to do today is to provide a little bit of context for the Walker Basin. It's also a very politically charged basin, and there's a lot going on right now. So I wanted to make sure everybody comes up to speed in terms of what's going on, at least from a hydrologic perspective, and then talk about some of the hydrologic modeling tools that we've developed for the region. And there are a lot of different types of models, not only hydrologic models, but water rights models as well. And then I'll touch on a few key results. This is a long study that's been ongoing since about 2009. Numerous team members and lots of different results and manuscripts and reports that have been written. So I can't really do this project justice in the limited amount of time that I have, but I'll do my best. Okay, so a little bit of context. Let's make sure everybody knows where we're at here. This is the Walker River Basin. For those that don't know, this is Walker Lake. Walker Lake is fed by the Walker River, which is shown here. There's two forks of the Walker River, the West Fork and the East Fork. What's important to note about this basin is that there is a lot of agriculture in the basin. The agriculture is primarily located in Mason Valley, so this would be near the town of Yerington, Smith Valley here, and then those are the two valleys in Nevada, and then there's also some agriculture in California, so that would include Bridgeport Valley, just above Bridgeport Reservoir, and then Antelope Valley, just above Topaz Reservoir. So those are the key valleys in terms of agriculture that use a majority of the water in the system. So then the question is, why are we studying this basin to the degree that we're studying it? And really the main reason is that Walker Lake levels have been declining since basically about 1910, 1920. So that's what this hydrograph is showing. On the x-axis, we have the year or the date, and on the y-axis, on the left-hand side here, we have the lake level for Walker Lake. So as you can see, Walker Lake levels have been declining on the order of about 150 feet over the last century or so. And then associated with that decline in lake level, there's been a very large increase in salt concentration in the lake. And that's what is shown here on this left, or excuse me, the right y-axis. This is the TDS concentration in milligrams per liter or parts per million. So as you can see in the 1880s, the concentrations, the TDS concentrations were on the order of about 3,000 parts per million, and then they've rapidly gone up to above 10,000 in about 1970 or so. And actually not shown on this graph, the most recent measurement that I was able to obtain was in 2014 that showed TDS concentrations about 23,000 parts per million. And for reference, sea level is about 35,000 parts per million. So this is a very salty lake. And it's my understanding that the main fish species in the lake, the Lawton cutthroat trout, is able to survive somewhere in the maybe 10 to 15,000 milligrams per liter range. So we've clearly exceeded that. So the cutthroat trout populations are essentially non-existent at this point. So given the large decline in lake levels in Walker Lake, the federal government decided to come in and put some money into the issue to solve the problem with lake levels. And actually in 2009, Congress passed Public Law 11185, which started the Walker Basin Restoration Program. And this basically allotted $200 million or so to purchase water rights from the agricultural community primarily, to send those water rights to Walker Lake to essentially to restore the lake. So that's the people in charge of this is the National Fish and Wildlife Foundation, or NIFWF. They have been charged with managing the $200 million to purchase the water rights and to help understand the system. So they've funded UNR and DRI and others to help develop these tools to help them decide which water rights to purchase in the basin. I also wanted to provide a little bit of additional context about the basin. And you guys may have heard recently about some things that have been going on in terms of groundwater levels. And recently, the state engineer, well, not recently, the state engineer actually monitors groundwater levels in Smith, on the left, Smith Valley and Mason Valley on the right. They monitor water levels on an annual basis. So I wanted to show you what's actually happening in terms of groundwater levels. I'm going to use Smith Valley as the example, but the results or the water level declines are similar for Mason Valley. So that's what's shown in this hydrograph. This is on the x-axis, we have the date. On the y-axis, we have depth to water for reference. So you can see that on a long-term basis, there's been declining water levels on the order of about a foot per year since this graph, when they started monitoring water levels, about 1980. But perhaps more importantly, since the last 4 years, because the system and others in the West have been at a very severe drought, water levels have been declining on the order of 12 feet per year. And to give you just a reference, or perhaps if you're not a groundwater hydrologist, you know, is this a rapid decline? And I would say it's a very rapid decline. As an example, in the South Truckee Meadows, where there's a lot of domestic wells and mixed in with municipal wells, you see groundwater declines on the order of perhaps 1 to 2 to 3 feet per year, but here we're seeing on the order of 12 feet per year. So these groundwater declines are similar to what we're seeing in California, where we have very few surface water supplies, so we have to move toward groundwater supplies to make up for the lack of irrigation water. So what is the state engineer and other Nevada regulators doing about this? So you may have heard, actually just a few weeks ago, the Nevada State Engineer's Office just issued this order for Smith and Mason Valley that it is further ordered that during the 2015 calendar year, all supplemental groundwater rights are curtailed by 50% of their annual duty. Now, what is the annual duty? The annual duty is 4 feet per year. So, and the other important thing to point out is this key word here, supplemental. If you don't know what supplemental groundwater rights are, these are typically in agricultural areas. The farmers that have supplemental water rights, groundwater rights, have the ability to pump groundwater when they do not have enough surface water as an irrigation source. So what happens in drought times? Well, if you're a junior priority right holder, they're going to be pumping a significant amount of groundwater in the system. Now, they're not going to be allowed to pump the full allotted amount, at least according to what they have on paper. They're only going to be allowed to pump 50% of their annual duty. And this has very significant effects in this agricultural community because you have many farmers and irrigators that rely on this source of water. But if you go back to this slide, the state engineer really had no option. They had to do something about these drastically declining water levels. And the only thing they could do was to curtail the pumping. Okay, so that gives you a little bit of context about what's going on in the basin. Let's talk about some of the tools that we have been developing to help us understand and manage the system. So since 2009, UNR and DRI and others and the USGS have been developing a variety of hydrologic tools. And specifically, we have been developing watershed models using the PRMS software system to simulate the headwater area. So this is simulating precipitation, snowmelt, and then runoff so that we can generate runoff downstream to understand how much water is available downstream. Next in line in terms of the water models that are available to us are water right models. And these are very important in these basins because there are a lot of surface water rights and groundwater rights holders in the basin. And what these models allow us to do using the ModSim software environment is allow us to understand the priority of these rights. So specifically, we need to understand which water rights holders are more senior, which are more junior, and exactly how much water is available to them. And then once we understand the water rights, then we have to understand what's happening with the groundwater system. As I said earlier, a lot of these irrigators are using groundwater as their source of irrigation, so we need to understand how groundwater is playing a role. And as you can see here, there's an arrow going from the groundwater models to the ModSim or water rights models back and forth. So what's important about that arrow is that information has to be passed from one model to the other. And we do this from time step to time step in the model so that, for example, when we know how much water is diverted to an irrigator, then if they don't receive enough water for irrigation, then a certain amount of groundwater has to be pumped. And then if you pump a certain amount of groundwater, we need to know how that affects the river flow. So that, because that could ultimately downstream impact water rights holders downstream. So all of this information has to be integrated seamlessly to understand the system. Now, what I've got here is an animation showing some of these hydrologic models and some of the information that goes into the models. And hopefully I can keep up with the animation. I think some of you have seen this before in the past, but it does give a pretty good overview of what's going on. So we're looking at now the entire watershed. That's Walker Lake there, and we're going to zoom in on some of the upper watersheds where most of the water is developed from precipitation in the Sierra Nevadas. And again, we have watershed models. This is the grid for the watershed models that help us understand how much runoff is occurring. Now we're moving down into Antelope Valley. This is one of the first key agricultural valleys in the system, and we have all the ditches, the surface water rights, the ditch point of diversions, et cetera. All of this information is in the ModSim or the water rights model. Moving downstream now into Smith Valley, we have all of the same information: ditches, drains, so drains drain water off the field so they don't become waterlogged. We have all the surface water rights. Groundwater wells, because now groundwater wells become very important in Smith Valley, points of diversion, et cetera. This is Artesia Lake off to the left. Moving down to the last main agricultural valley, we have ditches and drains again, surface water rights, groundwater wells, again, a substantial number of groundwater wells, and a lot of these wells are supplemental groundwater wells, pumping only in years of low flow. And we also have delineated each ditch system. So we subdivide the system into a ditch, a diversion ditch system, and we calculate water balances at that level. So we don't actually calculate water balances at the farm level, and that's actually done for legal reasons. And then Wabusca is a downstream gauge from Mason Valley. This is where we transfer off the model to to the USGS, and they have a groundwater model of this whole lower section here, down all the way into Walker Lake. Okay, going into a little bit more detail about these models. As I said before, the ModSim model, the water rights model, is directly linked to the groundwater model. And this fairly detailed schematic shows somewhat how this is done. And basically what's happening here is that a water balance calculation is being done at that ditch level scale so that we understand how much water is being diverted off of the main stem of the Walker River. It goes into what we call an HRU, or a hydrologic response unit. And a hydrologic response unit is just that area defined by a ditch that provides water for a number of farms. And then we have to make a number of calculations. We have to know what the demand is, or how much crop evapotranspiration is occurring, so how much water is lost from the system, how much actually returns back to the river via those drains that I showed you earlier, and then how much groundwater pumping is making up for the lack of surface diversions to meet the crop ET demand. And any excess water then either goes out as return flow via the drains, or perhaps as irrigation recharge, becoming groundwater recharge to the system. And that's a very important component. We need to know how much groundwater recharge is occurring, because that's the amount of water that's recharged in the aquifer during very high flow periods. So from a spatial perspective, it's important to point out where all the groundwater models occur. So as I said earlier, this is the lower Walker groundwater model that has been constructed by the U.S. Geological Survey and Kip Allender's group. And then we have two separate groundwater models, one for Mason Valley here, and then another one for Smith Valley. And we're actually currently in development of a groundwater model for the East Walker River to help us understand the agricultural diversions and supplemental groundwater pumping on that stretch. And then we're just beginning discussions with NIFWIF and others to build a model for Bridgeport Valley. The idea there being that there's, NIFWIF may have to purchase agricultural water rights in that region in California and send that down to Walker Lake. So we need to understand the hydrology better up there. Okay, in terms of what actually goes into, or what is needed to parameterize the groundwater model, there's a lot of information that goes into it. So these are all the pieces that go into the model. Let's look at some of the pieces in a little bit more detail. So recharge is a very important piece, and the three terms or three different components of recharge include the irrigation excess. So this is a photo of flood irrigation in one of the agricultural communities, and the idea here is that flood irrigation is highly inefficient, so a lot of that water then goes back and becomes groundwater recharge. Most of the ditches in both Smith and Mason Valley are unlined, so you get a lot of ditch losses in the system. That ditch loss becomes groundwater recharge to the system. And then lastly, you have mountain block recharge. So this would be natural recharge that's occurring in the mountain block. There's actually very little mountain block recharge in Mason Valley. It's a little bit more significant in Smith Valley, on the order of, I think, 15 to 20,000 acre feet per year, whereas it's only maybe 1,000 acre feet per year in Mason Valley. Of course, wells are very important, as I said, because as you draw or extract water from the wells, the water table declines rapidly. So we have the entire state engineer's well database, irrigation well database in the model for Mason Valley and Smith Valley. And these pictures are just to remind me that we're simulating the water extraction from the wells, but we have a whole nother number of monitoring wells where we're monitoring the water levels over time to help us calibrate these models. So this plot gives you some reference about how much groundwater pumping is actually occurring. In this case, this plot is this is for both Smith and Mason Valley, so it does not include California, although there's for example, in Bridgeport Valley, there's not a lot of groundwater pumping occurring. So on the x-axis, we have time or date, and then on the left-hand side, this is the Walker River flow rate, so that's this red line here, in acre feet per year. And I believe this is at Wabusca, so almost at the bottom end of Mason Valley. So you can see in good water years, you get about 500,000 acre feet of water flowing through the Walker River, but during drought years, it can go to perhaps 20-25% of that, from 500,000 to 100,000. And lo and behold, what happens, this other axis shows how much groundwater pumping occurs. So these bars represent the amount of pumping. So as the surface water supplies dwindle, the groundwater pumping goes up to make up the difference. And how much is that groundwater pumping? It's on the order of perhaps 40 to 50,000 acre feet in good water years, and above 100,000, almost as much as 120,000 acre feet during drought years. So groundwater is a very, very important component. But what's, I think, interesting about this plot is that because we go through high water years and low water years, the pumping varies substantially, as do the water levels. So the key is, how often are we going to be pumping significant amounts of water, and how often can we rely solely on surface water? Another important input parameter is basin thickness. We usually use geophysical tools, and I see John Louie, who was here earlier. He's helping us in Bridgeport Valley, collecting information on basin thickness. This is an example of basin thickness for the lower Walker section. So this is Walker Lake down here. So to give you an example of this scale, if you can't see it, the basin thickness for the basin fill sediments is on the order of about 1,000 feet in the lower system. Hydraulic conductivity is, of course, a really important parameter to input into the model. It governs the ability of water to flow through the system. We've parameterized hydraulic conductivity in a number of ways. In the lower system, this is the USGS model, they use a slightly more sophisticated approach where they are integrating aquifer test data. So aquifer test data provides hydraulic conductivity information at these red points. And then at the other points, they calibrate to hydraulic conductivity using what's known as a pilot point methodology. So the beauty of the pilot point methodology is it allows you to calibrate to these finite number of points, and you interpolate all of those hypothetical hydraulic conductivity points to the entire grid until you reach some level of agreement between the simulated and measured hydraulic head values. In Mason and Smith valleys, we used a slightly different approach where we used a zonation approach. So we used geomorphology to help us understand older and younger alluvial sediments and coarser sediments along the riparian corridor, and we can then parameterize the hydraulic conductivity based upon the types of sediments that we see. Phreatophyte evapotranspiration is really important in these valleys, particularly in the northern part of Mason Valley. So that's what this image shows, is the vegetation species in Mason and Smith valleys, with the yellow areas representing phreatophyte species such as rabbit brush and greasewood. And as you can see, they're pretty significant. We also parameterize the evapotranspiration for the riparian corridors, shown in red, and for wetland or open water sources. So this would be like areas associated with the wildlife refuge in Mason Valley and the Artesia Lake or the playa in Smith Valley. And as I said earlier, the rivers and ditches have to be simulated because they provide a lot of water to the system. And what's really important too is the interaction between the river and the aquifer. So we're using the streamflow routing package to help us simulate the interaction between the aquifer and the river for the Walker River, and we also do that for the agricultural drains, because the agricultural drains can also pick up groundwater. When the groundwater table gets higher and higher, you can actually get some seepage back into the drains, and that water is then carried back to Walker River. And then it's important to calculate the losses from the irrigation ditches themselves. These are handled separately, and that calculation is done in ModSim, or the water rights model. And then that amount of water that's lost from those ditches becomes a direct fluid source term in ModFlow. So it's not handled using the SFR package directly. Okay, so let's talk a little bit about some of the results that we found. And again, I'm just going to highlight some of the key results. The first here shows an example of a hydrograph comparison between the simulated and observed water levels. So on the x-axis, we have the date. On the y-axis, we have water level. And the observed or measured values are in the black line here, and then the measured values with the red line. So a couple of things to point out. I think the model is doing pretty good from a calibration perspective. We're able to match the trends quite well. But as you can see, there is an offset between these two curves, which is fairly common in groundwater modeling. And basically, this offset represents the general air that's found in the system. In this case, it's about a meter, maybe a meter and a half. So the overall air for the upper models for Mason and Smith Valley is, let's say, on the order of a meter, which is roughly about 1 to 2%, with 1 to 2% representing the air divided by the total head drop in the system. It's a normalized air metric that we use traditionally in groundwater modeling. And air's generally below 5%, or your model is doing quite well. So I think we're doing pretty good in terms of our ability to model the groundwater system in this case. Now, sometimes what people care more about is, instead of the groundwater levels, ultimately the mission or objective of the Walker Basin Restoration Program is to get water to Walker Lake. So we need to be able to model or simulate and predict lake levels in Walker Lake and also TDS concentrations. That's what this figure is showing. So this is a hydrograph, a simulated and measured hydrograph for Walker Lake. So on the x-axis we have date, in this case going back to about 1918, because this is when the modeling actually started. It was in 1918. And on the y-axis we have lake level in feet. So this part of the curve is the exact same curve that I showed you earlier, but now we have the measured values, so that would be the blue diamonds would represent the measured values, and then the red line would be the simulated water level in Walker Lake. So as you can see, we're doing quite well in our ability to simulate lake levels in Walker Lake. And associated with that, we also have to be able to simulate the TDS concentrations. So we do that using a fixed salt mass. If we know the lake level, then essentially we can apply a transfer function to get to salt concentration in the lake. And that's what is shown with these yellow dots, according to this y-axis over here. So we're doing quite well in terms of our ability to fit the model to the observed TDS concentrations. Now, usually when we are creating these models, people say, okay, that's great, you're able to calibrate the model, but they usually care about the prediction period. So let's talk about what happens in terms of predictions from the model into the future. So in this case, we took the model and we simulated it forward a period of about 60 years. So in this case, the model ended, the calibration period ended in about 2010, moving forward to 2068. And then we made predictions forward. So what do these predictions represent? These predictions represent moving forward in a status quo type condition. So that would mean that no water rights would be acquired at all. You'd just be moving forward, diverting water for agricultural purposes for the next 60 years. And if you were to do that, the predictions, and I should also point out that the river flows, we're using historical river flows to represent the boundary conditions for this model, so how much water is available to the system. So if the river flows were to remain relatively similar to what they have in the past, and agricultural diversions were about the same, the decline in Walker Lake levels would continue on into the future. And that is generally what is expected to happen. So if I can read this axis, I think it's an additional drop of perhaps 50 feet in the next 60 years, moving forward under status quo conditions. And then again, we can translate that into TDS concentrations in the lake. So under status quo conditions, we are predicting that we would cross sea level TDS concentrations actually pretty soon into the future, perhaps about 2040 or so. And then concentrations are predicted in excess of, or at least up to 60,000 parts per million 60 years into the future or so. And again, I'll point out we're already at 23,000, so we're already up into this range right here. Now, you can take the predictions and use those as if everything were to remain the same, But what is more interesting to water managers perhaps is what happens if you make some changes to the system. And as I said earlier, NIFWF has been tasked with purchasing agricultural water rights in the system, so they need to ask the question, if you were to purchase a certain amount of water rights, what's going to happen to the lake? That's a natural question to ask. And that's what these plots are trying to show or trying to predict using our modeling tools, is what's going to happen to the lake. So on both of these figures, on the x-axis we have water year. In this case, we're starting the origin from 2010, moving, again, 60 years into the future. The upper graph is a hydrograph of the lake stage in feet for various water right acquisition magnitudes or amounts. Okay, so this base level, the darkest red line here, would represent the status quo. That's the exact same line that I showed you earlier. So if no water rights were acquired. And then as you move up into these lighter red colors, you're acquiring more and more water. So let's look, for example, at the other end member. If you were to purchase 75,000 acre-feet of water, our predictions suggest that the lake levels would actually begin to stabilize and perhaps even rise a little bit 60 years into the future. Probably what's most important is which of these two lines produces a stable condition, and perhaps it's somewhere in between the 50,000 acre-foot to 75,000 acre-foot range. So that would produce stabilized conditions. And then again, we can transfer that information into TDS concentrations in the lake, and that's what's represented on this lower graph. So this is TDS concentrations in the lake in milligrams per liter. And the top of this axis is 60,000 parts per million. So everything would be reversed in this case. So the darker line on top would represent status quo conditions or no acquisitions. And then moving downward into the fainter gray colors, it's more and more acquisitions. So the bottom two here would represent 50,000 acre-feet per year of acquisition to 75,000 acre-feet per year acquisition. And this produces relatively stable TDS concentrations on the order of, say, 10,000 to 15,000 parts per million, which is basically the target level that NIFWF is trying to achieve. That would bring, hopefully, the fish species back and so forth. Another thing that we can do with the model is determine where the gains and losses are in the system. And this becomes very important from, say, the state engineer or the federal water master perspective, because once you purchase these water rights, generally they don't give you full face value of those water rights to transfer to Walker Lake. You get some portion of that, usually the consumptive use portion. But even once you achieve the consumptive use portion, let's say you purchase water rights in Smith Valley, perhaps there are some losses between Smith Valley all the way down to Walker Lake, and the managers need to know how much water is lost. And our modeling tools allow us to make those calculations. So for example, in this case, this is an accumulated gain and loss figure from 16 years of the transient calibration period. This gives us a general idea that for the cool colors, the blue colors, that Smith Valley is generally gaining, and then it transitions as you move through Mason Valley into a losing system. This information can become very helpful to understand what's happening throughout the basin. Another side project, I wanted to throw this in. This is something that Rosemary Carroll and I have worked on, is getting a better understanding of the evapotranspiration that is happening in the system. And as I said earlier, we are calculating or simulating evapotranspiration. And generally in groundwater models, the way we calculate ET is by developing a function of depth to water versus some evapotranspiration rate. And in the past, we really didn't have very good tools to parameterize these ET models. We're not botanists. We don't know all that much about vegetation, so we had very simple models. But now, as we have remote sensing tools to help us understand how much ET is occurring, we can get a better idea of how to simulate these in our groundwater models. So what we did is we actually developed a way to calibrate the groundwater models to allow us to achieve what we actually see in the real system in terms of evapotranspiration. So in this case, Justin Huntington used remote sensing techniques to quantify the evapotranspiration for these various vegetation communities, from saltgrass all the way to river riparian communities. And in some cases, as the red dots represent, we have well data that provide us depth to water information. So we know the ET rate, the actual ET rate, and the depth to water, and we can parameterize this in our models. And if we calibrate the models to this information, it provides much, much better simulations. And that's what this next graph is trying to show. This is just a one-to-one plot giving us a comparison of remote sensing derived ET values versus groundwater model simulated ET values for two different conditions. So Carroll et al. 2010, this is our first version of the groundwater model, in this case for Mason Valley. And what it's showing is that there is very poor correlation between measured and simulated evapotranspiration. In fact, you could argue that there's no correlation. And in a perfect world, you would have these dots line up on a one-to-one line, meaning the model is able to simulate the ET correctly. But when we included the remote sensing data into the mix and recalibrated the model, we got all of these color dots for the different vegetation communities. And as you can see now, we're bringing the dots closer and closer to the one-to-one line, suggesting that the groundwater model is able to simulate evapotranspiration more accurately. Okay, I wanted to include this plot in here. I see someone from the state engineer's office is here. I don't know if you've ever seen this plot before. This is not a modeling plot, so you might actually believe it. And what this plot is showing is measured groundwater pumping data on the x-axis versus net, what we call accretion or depletions on the y-axis. So you can think of this, and everything's above zero, so this is all loss. This is loss from the Walker River. So what does this mean exactly? As you pump more and more water, you get more and more loss. And how much loss is actually occurring? Well, it's actually a pretty good relationship. And what's interesting to me is that we actually had to lag this regression by 1 year, so we had to pull it back 1 year into the past, because that makes sense. It takes a little bit of time when you pump an aquifer. It takes a little bit of time for that system to draw down and begin actually pulling water from the river. So this says that if you pump on the order of, as I said before, we're on the 100,000 acre feet per year range, we're getting about a third of that lost from the river. And that perhaps has implications in a lot of different ways from legal perspectives, a lot of different interesting things may come out from these types of plots, not only in the Walker, but in other areas. This is a similar slide in a slightly different perspective. This is a modeling simulated graph, which is showing a date on the x-axis and then groundwater surface water fluxes on the y-axis. So anything above the zero line would represent gaining, so water going into the river. Anything below the zero line would represent losing. And I have two different conditions here. So the black line represents basically status quo conditions with SGP, that means supplemental groundwater pumping. So if we allow the farmers to pump groundwater in years where we don't have a lot of surface water, lo and behold, you get a lot of losing regimes in the Walker River. But if you were to turn off or remove all the supplemental groundwater pumping, the system essentially moves from a losing system to a gaining system. And that's what's shown here. It's very transient nature, but for the most part, the blue line, the no supplemental groundwater pumping, is above the zero axis, so you shift to a gaining regime. So groundwater pumping does have a pretty dramatic effect on what's happening in the river. And then this is the last slide I have for today. It's a pretty dense plot, and I'm trying to make a couple of points with it. So let's see if I can lead you through it. And perhaps it's backwards in the sense that the y-axis and x-axis should be shifted, but let's start with the y-axis. What this is representing is the reduction in irrigation area. So you can think of that as purchasing water rights, purchasing more and more water rights, and it's in metric units, millions of, it should actually be square meters, not cubic meters, because it's an area. But as you purchase more and more groundwater, or excuse me, as you purchase more and more agricultural water rights, associated with those water rights are supplemental groundwater rights, so you're pumping less and less water perhaps as you purchase those water rights. And then on the x-axis is the reaction of the system to that acquisition of water rights. So as you reduce the agricultural area, you increase the stream gains. And the two important features here are first that it's a slightly nonlinear response in the behavior. That is, it's not completely linear. And then the second thing is that it takes a fair amount of time for the system to respond to the change in the system, in this case, acquisition of water rights. So each one of these lines represents a different, basically decadal period in the simulation. So when you first acquire the water rights, let's say you acquire all of the water rights in the system, then you get a certain increase in stream gain, but for one period, one decadal period. But if you wait another 10 years, the stream gain gets larger. You wait another 10 years, the stream gains get larger. And it continues to get larger and larger, and it begins to stabilize a little bit. So this is important from the perspective, from a management perspective. And the question is exactly how do you use these modeling results? Which year do you choose? Do you choose the first 10-year period, or do you wait until it comes into some new equilibrium type condition? And what we've decided to do is actually, we've run this out actually 80 to 100 years, and we found that the system takes 80 to 100, in some cases, 120 years for the system to respond, the groundwater system to respond to changes in irrigation practices. So in terms of when NIFWF is monitoring what's happening to the river into the future, you have to keep in mind that there'll be sort of this lagged effect or delayed response effect in the system before you'll get full benefit from that acquisition. So they have to keep that in mind. So that's all I have for today. I'd be happy to take any questions you might have.